Hello students, let us take few more problems on moving charges and magnetism. 11th one is as follows. A wire placed along north-south direction carries a current of 5 ampere from south to north. Find the magnetic field due to 1 centimeter piece of wire at a point 200 centimeter northeast from the piece. So first, this is a question which is based on directions. So let us put the diagram of directions. Let me take this as north, south, east, west. So what we have is a wire along north-south direction. So this is where we have a wire. Okay? Yeah. This is the wire in north-south direction and it is carrying the current of 5 ampere from south to north. Okay. In this direction, this wire is carrying a current of 5 ampere. Find the magnetic field due to 1 centimeter piece of wire. Okay, just a small piece of wire shall be considered of length 1 centimeter, and due to this wire at a point 200 centimeter northeast from the piece. Let me consider the piece here. I can consider anywhere, but in order to get the proper point, proper position of the point, I am considering that 1 centimeter piece here. Okay, so this is the 1 centimeter piece that I have considered, and the point where we need the magnetic field due to this current carrying wire is 200 centimeter away and is northeast from the piece. So this is the piece, northeast. Northeast means exactly 45 degrees. Okay, how much? 200 centimeter, or I can call 2 meter distance, right, from here to here. This is point P where we need the magnetic field. Okay, so basically the formula for magnetic field due to a current carrying conductor, we can get the formula using two methods. One is by Bayes-Sauer's law, and the other is by using the Ampere circuit law. But here I am going to use Bayes-Sauer's law because Ampere circuit law can give the magnetic field at a point due to a very lengthy wire, or we can say that it is of infinite length. Okay, so and we will always consider the perpendicular distance, right? But now this is a situation where we have to consider a very small piece of wire, and the magnetic field shall be found due to this piece alone, not any other part of the wire. Okay, so I am going to you may use Bayes-Sauer's law to get the magnetic field at point P. And what are the given data? Given data is as follows. Current in the circuit is given. It is 5 ampere. And R, distance R from the piece to the point, right, which is 2 meter. Length of the piece, okay, the small length element which we call as length element, if you can remember, is also given, which I can take as DL, which is 1 centimeter, or I can call 10 to the power minus 2 meter. And we need one more factor here, which is theta. Okay, if you can remember Bayes-Sauer's law, okay, the expression for magnetic field due to this kind of wire is, remember, V is equal to 0 by 4 pi I dl sin theta by r squared, right? So here theta is the angle between I and dl and r, right? So this is our r, right? This is r. This is our dl. Okay, this direction. This is our dl, and the angle between them, okay, between dl and r is this. How much? 45. Fine. So dl and r theta is, and hence theta becomes 45 degree. Now you simplify for the solution. What is mu naught by 4 pi equal to? Mu naught by 4 pi is 10 to the power of minus 7. Current 5 ampere. The length element 10 to the power of minus 2 meter. Sine 45 degree divided by 2 square. Okay. What is sine 45 equal to? 1 by root 2. Okay. Make use of calculator. And get the value of P. Okay. So the value of P would be 8.8 into 10 to the power of minus 10 Tesla. 8.8 10 to the power of minus 10 Tesla. Yeah, we can consider this as dB. No problem. Even if you keep it as B, that's also fine. But it is kept as dB because the magnetic field at P, due to this small element, will also be very small. That is why we took dB instead of BC. Okay. So this is the small magnetic field that we get due to the small element that we have chosen. Okay. So this is about 11th question. Next, 12th question is as follows. A straight wire of length pi by 2 meter is bent into a circular shape. O is the center of the circle and P is a point on its axis which is at a distance 3 times the radius from O. A current of 1 ampere is passed through it. Calculate the magnitude of magnetic field at the point O and P. So this is a question based on a magnetic field due to a current carrying coil, isn't it? We need magnetic field at 2 points. One is at the point which is at the center of the coil, which is very easy for us, and the other point is at a distance of 3 times the radius. How much is the radius? Radius is actually not given. Basically, it's a straight wire of length pi by 2 meter, which is then bent to form a circular shape. Okay. Right, so I will not draw the circle like this, instead I will draw it like this, in this way, in this plane, because I need a point P, okay, a point P which is at a distance of 3 times the radius, 1, 2, 3 approx. So radius is also not given. Let me take the radius as R, and you all know that we took this distance as x, right? So remember the formula. And this point is O, right? Okay. What is given here? What is given is x is equal to 3r, right? 3 times the radius from O. Still comes the radius, and it is situated at from O. So what is given actually? A straight wire of length pi by 2. So the total length of the wire is pi by 2, which itself is the perimeter of the circle or the circumference. So 2 pi r is equal to pi by 2, right? So pi cancels, and hence the radius of the given wire is 1 by 4 meter or 0.25 meters. Fine. So we now got the value of radius of the coil, and now we can get x. X is 3 by 4 meter. That's it. And what is the current flowing through this? Current flowing through this is 1 ampere. So 1 ampere current is flowing through this. We need the magnetic field at this point and the magnetic field at this point. So we have the value of R, I, X and R given, and we need to get the value of magnetic field at these 2 points. Okay, let me work for the magnetic field at point P first. Okay, the expression for magnetic field at a point on the axis of a current carrying coil that we derived is given by V naught by 4 pi into 2 pi Ni r squared divided by r squared plus x squared to the power of 3 by 2. Right? This is the formula which we actually derived, and here n is the number of terms which will be 1 because we only have one term here because it's a single wire which is bent into this shape. Okay, so that's it, we can get the value. So since the point chosen is P, okay, we should rename it at point P, at point P, and hence you can put a subscript of P, magnetic field at point P is equal to mu naught by 4 pi is 10 to the power of minus 7. Simplify all of them. See, 2 pi is 6.28, n is 1, current flowing through that is how much? Current 1 ampere, right? Current flowing is 1 ampere into r squared. R is 1 by 4, which is 0.25 squared divided by 0.25 squared plus x is 3 by 4, which is 0.75 squared whole to the power of 3 by 2. Okay, make use of calculator again. Yeah, here you have whole to the power of 3 by 2. How do you get that? Square this, add them, you will get it out. Then multiply the term 3 times. Okay, after multiplying the term 3 times, take the square root of that. Okay, do all those things, and hence you will get the value. Finally, the magnetic field at point P given by 0.079 into 10 to the power of minus 6 Tesla. 0.079 into 10 to the power of minus 6 Tesla. Okay? Yeah, because of simple calculator. Okay, that's it. You can get it easily. Okay. So now it's time for you to solve for the magnetic field at the center O here. Okay, you should do that. What will happen to the formula? X becomes 0. It simply reduces to 2 pi ni by r. Right? 2 pi ni by r. Make use of that formula, and hence you solve for the magnetic field. Okay, you should do that. Don't forget to do it. Okay, very important one and easy one. So that's about 12th one. Okay, next 13th one is as follows. Two circular coils of mean radii 0.1 meter and 0.05 meter consisting of 5 turns and 10 turns respectively are arranged in concentric to one another with their planes at right angles to each other. If a current of 2 ampere is passed through each of them, calculate the magnitude of resultant magnetic field at their common center. Okay, so here is where we have two coils contributing magnetic field at a point. The two coils are concentric with each other. So far, concentric means the thought that comes to your mind is circle should be like this. Okay, not necessarily actually, because even if you have one of the circle like this and the other circle like this, even then you can get a pair of concentric circles, right? Somewhat like this. Right, so it's difficult to draw. Let me try. Yeah, oh, slow. Yeah, you can assume somewhat like this. Okay, two circles. Okay, even this is fine. One like this, the other like this, both with the same center. Okay, so one circle will be like this, the other circle will be like this. Okay? The planes are perpendicular. Even then, they lie on the same. Their center is one and the same, but the planes are perpendicular to each other. So let me draw it. Yeah, I've tried my best to represent two circles, two concentric circles with their planes perpendicular to each other, and is as follows. So I can consider this has a coil of 0.05 meter radius in, say, we call this as x, y and z. This coil is in xy plane, and the other coil of 0.1 meter radius is in the xz plane, okay, respectively, and are arranged concentric to each other. Then the center of both the circles is same, and with their planes identical to each other. If a current of 2 ampere passes through them, calculate the magnetic field. So now it's the application of vector addition. Okay. See, now we have two sources of magnetic field. One is this coil and the other is this coil. Both of them contribute for the magnetic field at the centers here, at the center. Now we should get the magnitude of that magnetic field from this and from this, and then we should get the vector addition of those two magnetic fields to get the resultant magnetic field at that point. Okay. So first, let us work for the magnetic field due to individual coils. Then we get the particular one. Let me name this magnetic coil, this coil of conductor as coil A, and this as coil B. So, question number 13. The expression for magnetic field at the center of the coil, we all know that mu naught by 4 pi 2 pi Ni by R at the center. So, we can directly take the formula. So, at point A, this is the general formula, write it once, that's enough. At, I can say due to coil A, okay, due to coil A, we have magnetic field BA, let me name that as BA, is equal to mu naught by 4 pi squared to the power of -7 into 2 pi 6.28. What is the number of turns in coil A? Coil A is the smaller one, which has 10 turns, right? The small coil has 10 turns into 10. Current through each of them is 2 ampere, right? 2 ampere divided by R, the radius of the smaller coil is 0.05 meter. Okay. Yeah, if you are confused with the data, you can write down the data once. That would give you more clarity. Radius of coil A 0.05 meter, and the number of turns in coil A, it is 10 turns. Current in coil A, okay, it is 2 ampere. That's it. Okay, you can take them as such and then put them here. So BA due to the inner coil shall be 25.12 into 10 to the power of -5 Tesla. 25.12 into 10 to the power of Tesla. 25.12 into 10 to the power of -5 Tesla. So this is about magnetic field due to the smaller coil. In the reference they have exchanged, they have taken this as coil A and this as coil B. There's no problem. You can take it. Right, let's go for the second coil B. Magnetic field at O, the center, due to coil B, okay, is equal to mu naught by 4 pi 10 to the power of -7 into 6.28 into number of turns in the bigger coil is 5, right? Into 5 into current in that coil is again 2 ampere divided by radius of the coil is 0.1 meter. Okay, again you can write the given data as such. Okay, if you want, that would give you more clarity, obviously. Okay, yes, keep an eye on that. That's good always. I sometimes avoid writing the given data. I directly take the data from the question and put that here. But it's good habit to keep the data. Okay. Keep the data. RB is 0.1 meter. Number of turns in the coil is 5. Current in coil B 2 ampere again. See, writing the data will not give you any mark, but it's only about the clarity of your question to apply the formula. To substitute for the terms in the formula, it's better for you. And the magnetic field due to that bigger coil is 6.28 into 10 to the power of minus 5. 6.28 into 10 to the power of minus 5 Tesla. This is the magnetic field at the center due to the bigger coil. Okay. So now you have two magnetic fields, BA and BB, due to two coils here, A and B. Now look, what is the direction of magnetic field produced by each of them? Say the magnetic fields produced, okay, each of them, they have not mentioned the direction of current, okay, clockwise and anti-clockwise. So no problem, we can directly consider some random direction. Let me take the direction here like this, and for this, let me take it like this. So now, let's see. Oh, sorry, the bigger circle is not in XZ plane, it is in what is this? Z by YZ plane, like this. Okay? Keep that in mind. Sorry. So right hand thumb rule will give you the direction of magnetic field due to each coil. For coil A, the direction of magnetic field would be like this, right? At the center, this is in XY plane, and hence, since this is in XY plane, the coil is in XY plane, normal to the XY plane is Z. So this is the direction of magnetic field due to coil A, which is BA. Okay, this is how BA look like alongside that. Similarly, for this YZ plane 1, okay, YZ plane 1, for the plane YZ, the direction of magnetic field would be like this in the X direction, right? So this is the direction of magnetic field due to this bigger coil B. What is the angle between them? Angle between them is 90 degrees, and you have BA, BB given here. The net magnetic field due to them is B is equal to, so it's all about vector addition, okay, and we only need the magnitude of the magnetic field, so don't need to worry about the direction of the magnetic field, it's only about the magnitude. So B becomes equal to root of, since they are perpendicular to each other, I can directly take a magnitude B squared plus B squared, right? Root of B squared plus B squared. Right. Put them here. 10 to the power of minus 5 is common, you can take it out. So it's root of 25.12 squared plus 6.28 squared into 10 to the power of minus 5. Okay, square them, add them, then take the square root, and hence finally you get 25.89 into 10 to the power of minus 5 Tesla. Okay. Right. So this is the net magnetic field, the magnitude of the resultant magnetic field at the center, which we can call as O, at the center O of the concentric circles given here. Yeah. You should visualize properly, then you can solve it easily. Easy one. Okay. Right. So the next question, 14th one, once again concentric coils. Let's see. Two concentric coils X and Y of radii 16 cm and 10 cm respectively lie in the same vertical plane. So this time we don't need to worry about the plane of the circles. It is like this itself in the same plane. Okay, wonderful. In the same vertical plane containing the north-south direction. Somewhat like in the same plane we can choose. Okay. Coil X has 20 turns and carries a current of 16 ampere. Coil Y has 25 turns and carries a current of 18 ampere. The sense of current in X is anti-clockwise and in Y is clockwise. Okay, here comes a tricky part. Okay, the sense of current in X is anti-clockwise and in Y is clockwise for an observer looking the coil facing west. Okay, give the magnitude and the direction of net magnetic field due to the coils at the center. Okay, fine. So first, let me consider the directions. It is given that the coil lies in north-south direction. Okay, right. So let me take the directions here. This is north, this is south, and the coils are in the same plane. So this is one of the coil and this is the other coil. There are two coils, one is of 16 centimeter radius and the other is 10 centimeter radius. Lie on the same vertical plane continuing to north-south direction. Okay. So here, see, this is north and this is south. I can choose this as west and that the other end as east. Okay, that's also fine because it's all about choosing the planes. Fine, let me draw it in a different way so that you can get everything here: north, south, east, west. Then the direction of magnetic fields. Everything should be coming here. Let me draw it in a different way. Okay, I have given my best in the drawing. Look at this. This is the plane containing north and south direction, right? And this plane has two concentric coils of radius 16 centimeter and 10 centimeter. Now, for a person looking at this arrangement from west, from here, it looks like the sense of current in coil X, which is the bigger one. Okay, this is coil X and this is coil Y. In the coil X, one can sense the current in anti-clockwise direction. So, for a person looking the flow of current from west, the current seems to be anti-clockwise. Okay, for the person here, current looks like anti-clockwise, like this. Okay, for the same person, current in the inner coil Y, looks like clockwise, which means exactly the opposite. Okay, so here, where is the observer? In which point is the observer? In which direction is the observer standing? All those things doesn't matter. The important thing that one should keep in mind is the current in the coils is opposite in direction, isn't it? One has clockwise, the other has anti-clockwise. If you observe it from east, the other will have the clockwise, one will have the anti-clockwise. That's how it is. Okay, so the basic thing is the fields are opposite. The current directions are opposite, which will produce opposite magnetic fields. Okay. Yeah, we'll get to know how they produce opposite magnetic fields. Now let us move ahead and see the terms. Right, let me write the given data for this. Radius of coil X is 16 centimeter, 0.16 meter. Radius of coil Y is 10 meter or 10 centimeter, 0.1 meter. Same vertical plane. Coil X has 20 turns. So number of turns in the coil X, which I can call Nx, is 20. Number of turns in the coil Y is 25, and current that is flowing through coil X is 16 ampere, Ix is 16 ampere, and current flowing through the coil Y is 18 ampere. Okay. Now we need to get the net magnetic field at the center. So formula is simple again. The magnetic field at the center of the current carrying coil is mu naught by 4 pi 2 pi Ni by R. Right? Make use of formula for both coil Y. A coil X magnetic field to that shall be taken as Bx, which is equal to 10 to the power minus 7 into 6.28 into number of turns is 20. Current into that is 16 ampere divided by radius is 0.16. Yeah, make use of calculator and get the value of Bx. So the value of Bx that you get is 4 pi into 10 to the power of minus 4 Tesla. 4 pi into 10 to the power of minus 4 Tesla. Similarly, for coil Y, you do the same way, put the values of all of them. You should simplify, okay? Do not avoid the steps. Put the values, everything you put, do the calculation properly, and then put the value of By. So By is found to be 9 pi into 10 to the power of minus 4 Tesla. 9 pi into 10 to the power of minus 4 Tesla. Now look at the directions of Bx and By. See, X is like this, right? And the current through the coil X is like this, which means the magnetic field due to coil X is towards west, right? So this is the direction of Bx. And what is the direction of magnetic field due to the inner coil Y? Look at this. Yeah. Last time I've taken them the same way. So for the person here, this is anti-clockwise, so this should be clockwise, right? Like this. Oh, sorry. Yeah. So now the field is exactly the opposite, like this, towards east. So this is the direction of By. Okay. Now look at the vectors Bx and By. They are exactly opposite each other, and hence the magnitude of their resultant would just be the difference of them. So B is equal to Bx minus By. Modulus of that, anyone is fine. So you, or By minus Bx is also fine. Okay, it's only about magnitude which is asked. Yeah, magnitude and the direction. We'll get the direction, no problem. But first we'll get the magnitude. So By minus Bx. Reason I wrote it as By minus Bx is By is greater than Bx. That's why. Okay, I'm working for the magnitude first. By is 9 pi into 10 to the power of minus 4. Minus Bx is 4 pi into 10 to the power of minus 4. Make use of calculator and hence you get 5 pi into 10 to the power of minus 4 Tesla. So this is the magnitude of resultant magnetic field. What about the direction? Look at this. These two are two vectors in opposite direction. The vector which is dominant will give the direction of resultant. Out of Bx and By, which is the dominant vector, By is the dominant one, which has the magnitude of 9 pi into 10 to the power of minus 4. And hence the resultant will also have the same direction as of By, right? We all know that. So this much of magnetic field towards, what is the direction? Towards east, right? Towards east. And hence this completes the answer. You should keep the direction, that will carry 1 mark. Okay? Magnitude and the direction, we can. So that's about 14%. Two coils in the same plane, but carrying current in opposite direction. Okay? Okay, 15.1. It is similar to the previous one and the previous one. But again, here they have not made use of current directly. They have given us an electron revolving, okay, single electron revolving in its orbit. Fine. 15.1. In an atom, an electron encircles in an atom. An electron encircles in the path of radius of 5.1 into 10 to the power of minus 11 meters. Okay. producing a magnetic field of 13.4 Tesla. 13.4 Tesla is a huge magnetic field actually. Okay. At the center of the orbit. The charge of electron to be 1.6 into 10 to the power of minus 19 coulomb. Calculate the frequency of the electron in its orbit. Okay, what and all is given? The charge that is moving is an electron, which will have a charge of 1.6 into 10 to the power of minus 19 coulomb. Negative. And this is moving in a circular path of radius 5.1 into 10 to the power of minus 11 meter. The produced magnetic field due to this revolution of electron is found to be 13.4 Tesla. Huge magnetic field at the center of the orbit. The charge of electron we need to find the frequency of revolution, mu. Okay. Fine. So we have magnetic field given and the frequency of revolution is asked to find. How do we get that? Frequency of revolution of an electron can be found if we have the current due to that electron, isn't it? If we have the current is Q by T. For one revolution, Q is equal to E, small t is equal to capital T, time period, right? So our aim would be to find I first, and making use of I will get mu. Fine. So to get I, we will make use of the formula of B. So this is an electron in its orbit, right? Of certain radius r. So if the electron moves like this, there will be current in this direction in the same path. So B is equal to mu naught by 4 pi 2 pi, the same formula Ni by R. At the center, this magnetic field will be produced. If we have taken at a point from the axis, at a point on the axis, at certain distance from the center, it will be 2 pi Ni R square by R square plus x square to the power of 3 by 2. You know that, right? Since the point is exactly at the center of the loop, we will simply take the formula of mu naught by 4 pi 2 pi Ni by R. And out of this, we need I. Magnetic field is given to 13.4 Tesla. Mu naught by 4 pi is 10 to the power of minus 7, 6.28 into, okay, number of turns 1. Okay, it's only one electron in the orbit. Into current has to be found, divided by the radius is 5.1 into 10 to the power of minus 11. Okay? Yeah. Make use of this data, simplify it, and get the value 5. I, that we worked at is 1.088 into 10 to the power of minus 3 ampere. Okay? So this is close to 1 milliampere of current due to one electron. Remember that. Okay? So considerably good amount of current due to that small in that small region due to a single electron. So this much of current is produced. Now what is I is equal to? I is equal to Q by T, charge by time. For one revolution, Q becomes E and small t becomes capital T. Isn't it? So take it in the bracket for one revolution, Q becomes E, small t becomes capital T, time period of revolution. I hope you know this. So now what is 1 by T equal to? 1 by T equal to mu. So I simply becomes equal to E mu. So mu becomes equal to I by E, which is I is 1.088 into 10 to the power of minus 3. Charge of electron 1.6 into 10 to the power of minus 19. Make use of the data. So in 1 second, the electron is undergoing 6.8 into 10 to the power of 15 revolutions. 6.8 into 10 to the power 15 hertz. Okay, this is the frequency of revolution of the electron in its orbit. Clear? Right.